Welcome back. So now we'll start with our homework assignment. Namely, we have to figure out what this quantization map is. And the quantization map I'm choosing is called Weyl quantization. And let me first specify what kind of problems occur when quote-unquote quantizing classical observables. This problem is literally as old as modern quantum mechanics itself. And if you read for example, the early edition of Dirac's book, then he spends a great deal on this. Because it was and is a conceptually important point, especially when you want to connect the classical to the quantum world. Because after all, if you want to look at it this way, if you have a classical observable with a semiclassical limit, this justifies why you can call the associated quantum observable by the same name. So for example, quantum angular momentum is the quantization of classical angular momentum. And at least under certain circumstances, you can prove mathematically rigorously that in the sense of the Egorov theorem, the classical angular momentum observable is the semiclassical limit of the quantum angular momentum operator, and hence it is justified that we call the quantum observable the quantum angular momentum. So this is conceptually very important, and the same of course goes for the energy observable, the Hamiltonian. It's exactly the same thing. So let me first start with some of the basics. So I think I always like to start with what I call the building block observables. And these are just position and momentum. So, for example, in position representation using microscopic units, this is just epsilon times multiplication with x. And the momentum operator is just minus I gradient. And so this quantization map, as I indicated before, should map the classical observable xj onto qj and the classical observable xij, which is momentum, the jth component of momentum, to pj. And these are characterized by the commutation relations, in this case the canonical commutation relations. Importantly, the commutation relations do not change when we change representation. So for example, if we use macroscopic units where the epsilon moves from here to here, the commutation relations are the same, and hence all of the Weyl calculus before quantization is also the same. So this is quite important. So these commutation relations, of course, we've seen them already, but now let me just rewrite them slightly differently with the prefactor I divided by epsilon. Then, of course, different components of position and different components of momenta commute. And if you look at position and momenta along the same direction, then they no longer commute. And because I put the prefactor I divided by epsilon in front of the commutator, for reasons that will become clear in just a second, I get minus delta Jn. So I get a minus here, and there the epsilon is absent on the right hand side because I've pushed it on the left hand side. And this is the quantum analog of the classical Poisson bracket relations. Well, here it's xj, the Poisson bracket of xj and xn is equals to 0. The Poisson bracket of psi j and psi n is equal to 0. So this is because one of these two functions is always derived with respect to momentum, or here one of these functions is always derived with respect to position, which means you get 0. And then the Poisson bracket of xj and psi n, that is equal to minus delta Jn. And again, you see the similarity, well, the correspondence between I divided by epsilon commutator and the Poisson bracket, which was one of the central points in the proof, right? Because also here, at least up to higher order, I divided by epsilon commutator and the Poisson bracket correspond to one another. But of course, this is, let's say, a vague, intuitive statement that basically we need to exploit further and explore further. So, but the conclusion is that there is a correspondence between these two guys. So this is related to point 2. And then there are cases where the quantization is, at least from the point of view of physics, is a completely solved problem. So the quantization of what I call simple observables of course, with uncontroversial, I mean these have been tested by physicists and they just work, period. So one example that came to mind is if the Hamiltonian is the sum of kinetic energy that only depends on momentum plus a potential that only depends on position, and that gets mapped onto, with the quantization map, onto the kinetic energy quote unquote evaluated at P. Of course, you just use functional calculus because the momenta commute amongst one another. I can also cook up a functional calculus for D mutually commuting observables. That's not an issue. That's, for example, in Reed-Simon, but it's very easy to do. And then you have the potential evaluated, quote unquote, at Q. Again, using functional calculus and so forth and so forth. So the reason, as I said, is the QJs and the PJs commute amongst one another. I should be very careful here. So the QJs and the PJs commute amongst themselves. So of course I did not mean to imply that that Q and P always have to commute. That's of course false. And now for all other operators, well, for the case where the function, so to speak, mixes x and psi, we run into what physicists call the operator ordering problem. Let me just give you a simple example. A simple example that can be resolved, but nevertheless illustrates a broader point of view, because even the resolution, it's clear that this does not extend to general functions. So the simplest example I can think of is just x dot psi. And now we really have a choice here. We could, so the quantization map could map x dot psi, for example, onto q dot p, which is, okay, so this is just shorthand notation for the sum of qj pj. By the canonical commutation relations, these two guys do not commute, so this is different from p dot q. Of course, the other way to do this is to quantize it to p dot q, which again is different from q dot p. But there's an infinite number of possibilities, and another one that I think is worthwhile talking about is the symmetric choice, where I just use 1/2 q dot p plus 1/2 p dot q. And the last choice has the advantage that it is, at least formally speaking, self-adjoint. So the symmetric choice is certainly appealing. So so here symmetric is of course a play on both the fact that this is a symmetric choice plus that this gives a symmetric operator once you choose a suitable domain. For example, smooth functions with compact support. So the symmetric choice is appealing, but not the only one. So in fact, there exist variants of Weyl quantization that implement different operator orderings, but what is commonly known as Weyl quantization indeed implements symmetric operator ordering. All right, so this solves the problem for this particular polynomial. Indeed, you can sort of extend this recipe of choosing symmetrically, for example, to other polynomials. But what about functions that are not polynomials of x and xi? And here the simple recipe is, well, simply too simple. So let's get some inspiration elsewhere, and that is that what we would like to do is, so if you look at the literature, for example, the book by Dirac, what he does is he writes f is mapped onto f of q and p. But he doesn't really explain how to solve the quote-unquote operator ordering problem. But what we can do is we can just think a little bit with the knowledge that has since been developed. We can just say, okay, this looks like a functional calculus. And this is not just any functional calculus, but a functional calculus for non-commuting family of operators. And that's already the good idea that you should pursue. So let me give you an idea how to express this in a compact way and introduce necessary notation at the same time, and that is the so-called symplectic Fourier transform. You can do everything with the usual Fourier transform, but it has one big advantage. So this is exactly like the usual Fourier transform, but it is an involution. So let me call this f sigma. And this means that I don't have to distinguish between the symplectic Fourier transform and its inverse, and this is tremendously helpful. This is really, really, really helpful. Okay, of course, you will ask, okay, what does it look like? Well, it really looks like the usual Fourier transform in most ways. So let me remind you that I'm using capital letters to denote the collection of position and a momentum. And this is defined as, we have the prefactor that we would expect to make it unitary in the right circumstances, because phase space is a 2D dimensional space, so 1 over 2 pi to the power d is exactly the right prefactor to accomplish that. And then we integrate over phase space. And I'm going to introduce another notation here, sigma of x and y, f of y. Before you want to know what it is, this is really just a variation of the usual phase factor. So this is e to the plus I psi. Oh, will it fit? Yes. Psi dot y minus x dot eta times f of y and eta. So let me, because maybe this is a bit small, let me write it a little bit bigger. So this is psi dot y. So you pair a position with a momentum with a position minus x dot eta. So what it does is two things. So the symplectic Fourier transform has different signs for the integration in y and in eta. And furthermore, if you look at it closely, it flips the entries. So here on the left, there's always a position variable, like here. And on the right, there's always a momentum variable. So these are the two things that you do. And hence, it's clear that this inherits all the properties of the usual Fourier transform and so forth. And starting from that, I can just do the following. I can write out f sigma squared evaluated at x and psi. There should be a squared here. And this is what, and I'm only writing out one of the two Fourier transforms. I'm keeping the other one implicit. And then, okay, I have my phase factor here. And then I have to multiply the symplectic Fourier transform of f evaluated at y and eta. So now if I look back at the notation you can find in older physics books, we can just make this into a definition. And this is indeed the definition for Weyl quantization. So what I'm going to do is, let me also write it in a second way where the analogy becomes more obvious. So what I will do is, so this here is of course f of x and xi. And this is, by definition, the Weyl quantization of f, which is defined as, well, it's the same as the equation above. And the only difference is that in this exponential quote-unquote phase factor, I replace xi by p and x by q. Of course, we have to make sure that this really makes sense, right? But this is the good idea. So let me place a little bit of additional emphasis on it. So you basically replace this here by this here, and that's it. This choice, as I've mentioned before, leads to symmetric operator ordering. You can implement the other operator orderings by replacing this single exponential by, for example, if you want p's to the left and q's to the right, then you can just replace it by two polynomials. One is this guy, the other one is that guy, and so forth. And of course, this is permissible because you can do this factorization on the level of functions here. But of course, this factorization is not allowed because not all of the p's and q's commute. Well, yes, exactly. The second thing is, and I'll just add this as a comment, the way you would define this integral is in the strong sense as a Bochner integral, as an integral of a function that takes values in our Hilbert space. And here, you know, if you really want to dig down deep, you have to pay a little bit attention to the notion of measurability that you're using. It's not as simple as the one for functions on R or on C, but c'est la vie. So this is the good definition. It is suggested by history, and you know, it is completely developed mathematically. The central piece, and I will just because it's so important, I will tell you its own name, is the so-called Weyl system. And this is the unitary operator in red. And let me just write out the action of the Weyl system. On an L2 function. So this is no longer a definition, this is just a consequence of a computation. So if you want, you can also write e to the minus I sigma y, capital Y, and qp applied to psi evaluated at x, but this is just the operator in red. And if you use the Baker-Campbell-Hausdorff formula, for example, because the commutator of pj and qj is proportional to the identity, you're allowed to do this. You can easily convince yourself that what you get here is e to the I epsilon eta times x plus y over 2 times psi of x plus y. So this is just the result of a computation. And with this, it is helpful to write out the action of op f onto a function psi. So we will use this later on. So op f applied to psi evaluated at x. If you do some very straightforward computations, then this is equal to 1 over 2 pi to the power d, integral in dy, integral in d eta, then you have a simple phase factor, which is e to the minus I eta times y minus x. And then you have f evaluated at epsilon half x plus y in the position variable, and eta in the momentum variable applied to psi of y. And you can also rewrite this in a second way, which will be helpful when we want to extend the notion of Weyl quantization to more general functions and distributions indeed. We can just focus on the integration in the y variable. And this integral here, this integral here is nothing but the partial Fourier transform in the second component. So let me denote this with f2. I don't think I will reuse it, f2, but nevertheless. And it is evaluated at y minus x. And then you have to multiply psi of y. And of course, we borrowed a factor of 1 over 2 pi to the power d minus 2, d divided by 2, which is now implicit in the Fourier transform. And importantly, we give an abbreviation to the whole shebang, which is just kf of x, y, psi of y. And that is because later on it's useful, instead of characterizing op f directly, we can characterize the so-called kernel map where f is mapped onto kf. All right, so far all of these manipulations have been purely formal, and the easiest class of functions that we can study in this context are Schwartz functions. So as the name of this subsection implies, all functions are now assumed to be Schwartz functions. So we'll not write this out because that, would add up over time. So one fact that is relatively easy to prove is that the unitarity of the Weyl system implies the boundedness of the quantization of any Schwartz function. And the estimate that you do is, well, if we write out the definition of the operator norm, kill the supremum for the moment, then what we need to estimate, and let me fastidiously include the space that the norms are associated to. So here I'm looking at the L2 norm over our space RD. If we just look at the original equation, then this is a constant factor containing powers of 2 pi, just a prefactor. Then I have the integral in y of the absolute value of the symplectic Fourier transform of f times the L2 norm of the Weyl system applied to psi. But because the Weyl system is a unitary operator, this here is nothing but the norm of psi, again in L2 over Rd. And thus the right-hand side is actually independent of y, which means that we can introduce brackets here. And this here is equal to the L1 norm of f sigma of f. And because f is a Schwartz function, its Fourier transform, hence its symplectic Fourier transform, is a Schwartz function, and hence it has a finite L1 norm. And this is already the result, right? Because now what we have is 2 pi to the minus d times the L1 norm of f sigma of f sorry, it's not Rd, it's R2d. So that's why I wanted to write out the spaces. Let me fix that here as well. Of course, if you're feeling very charitable, you can estimate this in terms of the L infinity norm of f, which happens to be one of the semi-norms. So, you can make this more explicit if you want, but that's good enough, times the L2 norm of psi. And now we can take the supremum over all psi of norm 1. Norm 1 means this factor here cancels out, and we have found a norm on a bound on the operator norm. So this is a rather simple and crude estimate. You can also use more sophisticated arguments. To show that, that the Weyl quantization of a Schwartz function is actually a continuous map between Schwartz spaces. So what do I mean? Well, it is a continuous map between the Fréchet spaces SRD and itself. And another important thing that follows directly from the definition is that because we're dealing with bound operators, self-adjointness is the same as symmetry in this case. For bounded operators, and what we can show is that the adjoint of the Weyl quantization of f is equal to the Weyl quantization of the complex conjugate function. That's maybe a little bit hard to see here. Maybe let me write it out first. So op implements symmetric operator ordering. In the sense that, like I wrote before, the adjoint of the Weyl quantization is equal to the Weyl quantization of the complex conjugate function. So, at least formally speaking, x dot psi is a real valued function. So if we can solve the problem of domains, which we can, then this will Weyl quantize to a self-adjoint operator. So what do we have to do now still? Well, we have to extend the definition to broader classes of functions. And here the approach is to extend by duality. So what you do is you first extend Weyl quantization to tempered distributions. And because you can view many functions as a tempered distribution, then this means we have a definition, we have a way in, we have a hook into while quantizing functions that are not Schwartz functions. So here I would like to, in case this is new to you, I would like to recommend an article by Marius Mantoiu and Radu Purice from 2004. Again, you can find this in Microsoft Teams, or you can ask me by email, where they explain this very, very clearly in a very short amount of time. So that this is Mantoiu and Purice from 2004. And in particular, section 2 for the non-magnetic case, and the rest of the paper in case you want to know how to do it with the magnetic field. So the idea is that you replace Schwartz functions, either D or R2D, by tempered distributions. So let me maybe emphasize here that I'm talking about tempered distributions, and many functions and of course also L2 over RD. So for example, so the reason is many functions may be considered tempered distributions or define tempered distributions. So common examples are L2 over RD, which you can think of what I should do is something nicer here. So for L2 over RD, you can actually bracket it between Schwartz functions, which are dense in L2, and the tempered distributions. Another example that comes to mind are, for example, smooth polynomially bounded functions on R2D, which you may consider as a tempered distribution. So these are two common examples. How do you go about extending the Weyl quantization? So here it becomes clear why I introduced the kernel map. So because the extension of Weyl quantization is equivalent to the extension of the kernel map, and let me first write out what the kernel map is in words. So the kernel map is the composition of two maps. Well, it's also multiplication by a constant, but since we're all adults, I will just leave that out. So it's a linear invertible change of coordinates. Composed with a partial Fourier transform. Let me copy and paste the relevant equation. So the kernel map, as a reminder, is 2 pi to the minus d over 2 times paste. Now let's just color the ingredients correctly. So the partial Fourier transform is purple and the coordinate transform is green. So it is clear that linear changes of coordinates that are invertible extend to tempered distributions, and partial Fourier transforms do as well. So up to this factor, this constant prefactor, which is also not an issue, we can immediately explain why the kernel map, and hence Weyl quantization, extends to S prime over R to D. All right, so maybe you're still a little bit uncomfortable about this equivalence here, so let me make it more explicit. Any operator is uniquely determined by its matrix elements. And if you look at this here, this is already half of a duality bracket, because you still have to integrate over the x variable. So let me do this, but let me do this in a way that is compatible with quantum mechanics. So phi and psi are Schwartz functions. And instead of using the regular duality bracket, let me do it in a way that is a little bit more compatible with quantum mechanics. But in the end, what you get is kf, the duality bracket of phi complex conjugate tensor psi. And the reason is simple. If you write this out, then this is the integral over x of phi of x complex conjugate op f applied to psi evaluated at x. And okay, this just gives me the integral. Now I have two integrals, 1 over x, 1 over y. And now I have the kernel map. I have phi of x complex conjugate psi of y. So if phi and psi are Schwarz functions, then this expression here makes perfect sense. Makes complete sense. And it is in this sense that you can extend Weyl quantization. So thus you can view op f as a continuous function. And now we have to pay attention from S from Schwarz functions to tempered distributions. That is simply by looking at it. So let me. Sorry. So this is the duality bracket on R2D, but you could also view it as the duality bracket of op f applied to psi and phi complex conjugate. So it is in this sense that you can also define Weyl quantization for all tempered distributions. Of course, this is not the completely satisfactory. We would like to single out very nice distributions that have even better behavior. So while the above is certainly correct, for some special tempered distributions, or of course I'm mostly thinking of functions which are regarded as tempered distributions. But of course here the key point is that this is not a general fact, but this is something that needs to be proven. The Weyl quantization is continuous between S and itself. So the difference between these two is that here I have on the top I'm looking at tempered distributions, and in the bottom I'm looking at Schwarz functions. Before we marvel at this and think about what this means, let me give you an example of a class of functions that has this property. And those are the so-called Hermander symbols. So the order is M is a real number, and the type rho, well, this is also a real number, but it must lie between 0 and 1. And then I'm defining the topological vector space. In fact, it is a Fréchet space by in terms of the seminorms that I will give in a second. So Hermander symbols are smooth functions on R2D for which all of the seminorms that I will define in just a second are finite. And the seminorms depend on the order, but also on the multi-indices A and alpha. Well, what we do here is we take the supremum over all points x and psi in R2D. And then we need a prefactor that controls the growth. So this is just 1 plus psi squared. And I'm taking this to the power, this may be a bit hard to see now. I'm taking this to the power minus m plus absolute value of alpha times rho. And once you see what the alpha does, it's very easy. So I'm taking the the eighth derivative in x and the alpha derivative in psi. And okay, so what does this do? Well, this here, this prefactor here allows that our symbol to grow at infinity, but it controls the growth. So it must. So if a and alpha are 0, then this just says it does not grow faster than absolute value of psi to the m at infinity. And that is simply because this expression here behaves like psi to the power minus m plus absolute value of alpha times rho. As we go towards infinity. So, and every time we take a momentum derivative, our growth slows down by rho. So this is the point here. So you, if you start taking derivatives in momentum, the properties of your symbol improve, and eventually the symbol must actually decay in momentum. And this is evidently a very useful thing to have. And okay, for these simple symbol classes, so you can also define refinements. Nothing happens when you take derivatives in x. And let me just close this part too by saying that, okay, for Hermander symbols, it is true that their quantization gives us continuous maps between S and itself. So it's a continuous map on the Schwartz functions. And the reason is relatively simple to understand. The seminorms tell us that Hermander symbols are smooth, uniformly polynomially bounded functions, and hence, I can multiply them with Schwartz functions and so forth. Of course, the actual proof is more complicated. Let me just give you a hint. So, of course, we need to write out op f applied to psi. And the main obstacle here at least for if we claim that this is true for all m and all rows and deltas, and that is that in general the integral that we're worried about, which as a reminder is, for example, this one here. So this integral here does not, in fact, cannot exist as an absolutely convergent integral. So what do you do? Well, you introduce a more general notion of integration, and this was done, studied a lot by Hermander, for example, and these are oscillatory integrals. Just so that you have an idea that this, I'm not talking about the empty set here. The simplest example I can think of is the function psi squared, right? The claim is that this should quantize to p squared, which is perfectly well defined. But of course, this does not exist as an absolutely convergent integral. So what we have to do is we have to interpret the integral as a so-called oscillatory integral which is defined via a regularization procedure. And if you're not familiar with them, I've just this year held a lecture on oscillatory integrals, so was very good preparation for this mini course. So I will refer you to my lecture notes. From 2021. Okay, so once we have the correct notion of integration, the rest is just a matter of estimating seminorms, which you can probably imagine is perhaps a bit laborious, but conceptually straightforward, and that's exactly what it is. And that's the proof. And let me just add a comment that typically what you have to, what you would like is, if we're talking about functions like psi squared, unbounded functions that give rise to unbounded operators. So questions of domains have of course been studied. And the typical domains that you can expect are Sobolev spaces of order M. But then, for example, you would need something like ellipticity in addition. So ellipticity just means, so if you have a Hermander symbol of order M, then the function could grow in some direction like order M minus 1. But in the quote-unquote worst direction, it could grow like order M. And if a symbol is elliptic, then this means that independent of the direction that you're looking at, towards infinity, the function explodes like absolute value of psi to the power M. And then for elliptic functions, for example, they give rise to operators. Let's say elliptic real-valued functions. They give rise to self-adjoint operators where the domain is given by the mth Sobolev space. So if f is elliptic of order m, then and real valued, then op f defines a self-adjoint operator on the mth Sobolev space. Another important theorem in this context, and this will be the last thing, is the so-called Calderon-Vaillancourt theorem. And this says that if your Hermander symbol is in Hermander class S0, then this implies that its quantization is actually bounded. So you could these two theorems are of course connected. So when you prove one, then basically you have the other, and typically you start with the Calderon-Vaillancourt theorem, and then you compose the f with another operator that maps hm to, for example, L2, and that's the content of the proof. All right, this video has been super long, so that's it for Weyl quantization. Next we will talk about the Weyl product in part 3.